Okay, we're now live.
Okay, good.
Okay, hello. So today we're going to focus on quaternions and electromagnetism. So I suppose I'll just present the first thing we should look at is the kind of previous work to this, which is this. So we kind of went through this before. You can see that, can't you, Rajan? This paper. Hello, Rajan, you there?
Yeah. Okay. Yeah. So it is. Yeah. Full screen. It seems to be okay.
Oh,
I
good.
have to go full screen to see it. It's okay.
Oh, excellent. Okay, so here you go. This I can hide this over here, I think, and then enlarge this.
Okay.
There. I'll have to do that for all of them. So basically, the idea is to create the meridian, hypermeridians, and parallel lines on the hypersphere S3, and then stereographically projected. So the meridian lines and parallels form the electromagnetic, or the magnetic field lines, with one going to infinity using a stereographic projection. And then the green hypermeridians are meant to be in this model kind of electric currents. And so this paper sort of details how we might relate the Quaternion hyperspace model to well, more so along how we would relate it to Maxwell's equations, and just show that the two are kind of linked. So there we go. We'd have the quaternion. The geometry. Here's the fields information. We'd have the geometry, like I said, and because it's four-dimensional, it'll be a quaternion. And then we have the Maxwell sort of equations or link to that. So now this is useful for maybe possibly modeling the Earth's geomagnetic field, because by rotating it in 4D space, we can distort the field lines and create the kind of distortions that we might expect from solar wind and photon density, that kind of thing. But initially, we're trying to build a kind of a unified electromagnetic field using both the magnetic field vectors and electric field vectors. So this was kind of my first attempt. But we can see that there's some issue with this, because this is going outwards, but this is sort of orthogonal. So these field lines aren't correct. They need to be redone. And then we can generate sort of intensity plots. And then the final thing we can model is this idea of the solar wind sort of whipping one of the field lines over the top of the geomagnetic field so that it reconnects on the other side. Now, that's still a work in progress. This was just meant to be sort of a sketch idea. But where we're moving to today then is more taking a leaf out of this research, unit quaternions and electrodynamics. Now, this is a presentation done by the well-known YouTuber Alexander Unzicker, who has a YouTube channel called Unzicker's Real Physics. And this is a lecture that he gave, I suppose, a number of years ago, back in 2021 or thereabouts, or yeah, November 26th. So you can watch a bit of this, maybe.
Let's have a look at the action of right and left multiplication. Now it becomes interesting, because if you look closely, And if you do a multiplication first from the left, you see what's happening here. You're pushing the line here, the green line, you're pushing the line, and at the same time, there is a right turn in the JK direction. Vice versa, if I pull the line, the rotation is counterclockwise.
Okay, so that gives you the basic idea. So you can see he's using quaternions, left multiplications and right multiplications using just this basic formula here. Now, the interesting thing is he's trying to link this through electrodynamics. So we can imagine that the yellow line here is an electric current, and the circle ijk is actually this is 1 jk, and this is I guess. So this would be the magnetic field line. So as the current passes through, field line rotates, and that gives us the electrodynamics that we're interested in. Now, possibly a bit tangential is this video came to my attention as well, but it's got some kind of interesting graphics.
The number of electric field lines
it's almost a work of art. But you can kind of easily see the dynamics of the field in this video. It's quite visually striking what this person put together. So you can see here this these field lines, the green, and then they have these like circles. So this is almost identical to what we're going to create. And then, oh, have we skipped by it? Yeah, we did. Shows just different had the different shape. So this could be the planet Earth, but it doesn't matter what shape this is, the field will always have the same shape. And this is the charges running through the field lines, which will then, according to our model, then rotate. These green lines will rotate because as the charge moves through it. And we'll facilitate all of that by quaternion multiplication. And here's just another graphic, you know, showing the as these red balls, which are the current, move towards us here, the field is rotating counterclockwise, and if they move in the opposite direction, the field will move the opposite way. And so this line here is basically the same as the circle we saw on the other one. It's just stretched out. So this is identical to what Unzicker showed in his video with the straight line, which was I, and then the IJ, 1 IJK rotation lines. So that is basically the whole thing. And that's a good video. I haven't watched all of it, but I don't know. It's just interesting. Pretty funny. Let's move on anyway. Okay, so there's some notes. We've covered that. And so we might as well just get straight into it here, I think. So this
excuse me.
Yeah, go ahead.
Where does this publication, is it in the RG, this paper that you showed?
This, which one?
Yeah,
this
the one that you just now. Yeah, that one. Yeah.
Yeah, that's on RG. Yeah, I did or
this one.
to the G, R to the G, is it? Oh yeah, this is on RG, and then the what is it? Yeah, I think I sent this off to some journal, but I think they said it was out of scope, but it's basically just so if I fix some of the problems with it and maybe add more of the geomagnetic kind of element to it. I might be able to send it to a different journal, but who knows? Okay, so now all of this, basically what this does is it creates the hypermeridians and the meridians and the parallel lines, and then these are the quaternions. This is the multiplication, and then we project the loop. This is generating all the different curves that we need. And then there's an extra bit here because, I don't know. Okay, so we don't have that, but if I run the first of these, let's say this one, and I just make that bigger maybe. So you can see that as the red line moves downwards, the green parallel lines rotate around. Now the red ones are also going to rotate in the opposite direction. We've decoupled the hypermeridians, the blue ones in here that you can't really see. So they don't rotate in this model. But so in order to stop the red ones from rotating, we apply oh yeah, this is where it gets a bit tricky. We apply this parallel phase average. So you basically measure the phase and from like the static point and then rotate it the opposite direction. So you can stop one field from rotating based off the other field as it rotates. So that gives us a static method. Now all of these vectors on the field lines are dynamically produced in this model, which I'll give you a look at that. So it's using this Biot-Savart equation, which I believe, and this is more of the sort of dynamics that you have with sort of standard electromagnetic field theory from things like Maxwell's equations, and we've got the Helmholtz thing with the decoupling. Or actually, this is this is just a divergence clean. So all of that is supposed to create these dynamics, but as we can see here, it's quite messy. So we actually don't want that. So we'll get rid of that. All of that was kind of wrong. So the newer versions eliminate that. And what we do is we just take the, you just sort of sample on the field lines and then take the tangent to that field. And then, so oh, well, that still has Biot-Savart there for some reason, which we don't want. And this one, or maybe it's further down. Yes, yeah, this is it. So I think we're too big here, but normalize. Right, so we stereographically project it. This is kind of a push forward sort of thing. Generate the loops, and then we get the curve tangent. So that's what, so we're kind of sampling on the curve, and then we'll take the orthonormal, the orthogonal vector then from the magnetic vector. This all works. So, and then sign alignment generator, just to ensure that the arrows face in the direction of the rotation of the lines. That should be obvious anyway, but geometric arrows from loops in S3, and this just basically builds the arrows and normalizes them to ensure that they don't blow up. I think at the projective point, there's a rotation helper, and then we're sort of graphing it here. So I think that's really it. So that is that one. So we can have a look at a few of these anyway. For instance, this one that I made does what I was telling you earlier. It essentially stops the rotation of both of our meridians and parallels by taking the base and then rotating them against each other in a sense. So it cancels out all rotations. This one still has the Biot-Savart sort of dynamic field, which we don't want. So we can close that. Not sure what this one is about. Pretty much the same. Close that. This is just a different angle with, and then sort of muting the arrows, so it's a bit easier to see what's going on. One thing that we can see with this is that when it gets to this point, there's a sphere. These lines create a kind of a sphere in the center. So, I mean, otherwise, it's looking pretty good. You know, it looks basically the same as we saw in that video. We have the red meridians and circles in the center, so there's a current flowing through there, and currents up here as well, I guess. But you know, so this wraps to infinity. So it's a bit like the way the electric field force expands to infinity, which is kind of cool in a way. But I was thinking that, you know, if you have a magnet here and it's attracting at the North Pole and repelling at the South Pole, which is kind of what this this expanding thing seems to do. You can imagine it like a claw pushing away and pulling in. So, I mean, there are some videos online, like for instance on YouTube, of people who put iron filings suspended in liquid, and then you can slide magnets into the sort of into a cavity in the liquid jar, so that you can then see how the magnetic field lines interact with the sort of 3D environment of these suspended metallic iron filings. But yeah, and in a previous video I saw they were kind of, you'd see some of the filings move, and then they'd move into place, and then there'd be a brief sort of window in a sense, and then the next layer of filings would move. But actually, looking at it more generally, I don't see that. They all kind of seem to move more or less at the same rate until you get to the point where all of the filings are sort of in place already around the magnet, really. And then once that occurs, then you might see some stragglers that move in. So initially I was thinking that that this kind of phase wrapping thing that's going on, where it's like periodic, would be the mechanism that would explain why the iron filings are moving almost like, you know, single file, like one after the other in a sort of step kind of wise function, or something that's staggered, you know, and that this periodicity would explain why that was occurring. But looking into it more closely, I don't really think that's a thing. So yeah, aside from maybe explaining why there's this push and pull factor on the magnetic field lines, I don't think it's really that necessary. But even so, we'll move on to a more accurate version. So let's see what this one does. Or did we already look at this? No. Okay, so in this instance, this is without the dynamic magnetic field lines. This is so the Biot-Savart thing is gone, but we do notice that we've lost here that all of the field lines are rotating. So it's a bit more confusing. So we'll get rid of the rotation, I think. this one is anchored. Yeah. So what have we got? So here we have the purple vectors are the tangent. So that shows the B field, and then the cyan, the kind of blue vectors are showing the electric field because it's meant to be orthogonal to the B field. And then the gray lines there are, oh, well, actually, I should mention the orange vectors on these parallel lines they're also the electric field, okay? And then the gray ones are, because we have a four-dimensional field that's being projected from, Quaternion space down into R3. We also have a fourth vector, which is now the gray ones. So, yes, and so if we think we have, so if the orange ones are,
excuse me,
yeah,
where are the gray vectors? Can
they're
you
a bit
point
hard
to
to
it?
see, but can you see my cursor here?
Uh-huh.
Okay, so you should be able to see a gray one moving across my cursor there. Every
Oh, okay.
oh, crap, they're on the red curves.
Ah, okay.
Along with the blue and the purple ones. Okay, so that's a 4D vector, and it doesn't really have a name. So if you think about it, I believe the cyan and orange ones are both E field, and then the cyan and the orange are E field. The purple one is B field, and and then the 4D vector. Oh no, actually, I think there's. Let's just have a look. Yeah. Okay, so this might help. You can see that the lines are now anchored. They're no longer rotating, which is handy. So what have we got here? So orange is E. The P is cyan. So the P is like the pointing vector, which is, and then we have S, which is E times B. So, and that's magenta. So what we notice is that we have the orange ones, they're the electric field. And then the cyan and magenta ones are overlapping. Basically, they look to be, there is a slight difference. Sometimes you can see the magenta one, the cyan ones overlapping the magenta ones, or they sort of appear and disappear. So there does seem to be some discrepancy between this pointing vector that's all of these are projected from 4D space, and the sort of E times B, or total field kind of force. So yeah, we'll have to look into that more, but see if there's any other visualizations here. So another interesting thing is all of this complexity that arises in the center of the field. There's a lot of curling and coiling going on, which is pretty interesting. I mean, that's the kind of thing you'd expect from some of these kind of complicated electrodynamics models, electromechanical or magnetic dynamics, and this sort of falls out of the process. It's not added in or anything, so it's pretty interesting. I mean, you can see the way the orange ones come out, and they curl in, and then they wrap around the center, and then they come back out at the bottom here. So I mean, it kind of looks like there's something. Yeah, like, because like if we were to track one of these, what is its path? You know, it seems to curl outwards here in an anti-clockwise direction, and then yeah, it sort of continues in an anti-clockwise direction, and then it goes in a clockwise direction. So it's weird. You know, I'm using various methods to. So which one is that? Is track. Okay, so this one should have a black. Oh no, actually, yeah, the track on that one is in the wrong place. So we'll check this one. So this is tracking along the parallel lines. So what we're looking for here is a vector that's kind of black. And that one, yeah, I'm just trying to track yeah, it seems to be okay. So we track the black one, and it goes in, and then it kind of goes around. So yeah, I'm wondering, is this not slightly different to the other one that we have? So it might be sort of worth investigating whether it's, yeah, whether it is correct or as correct as the previous one. So let's see, if this one was track parallel, excuse me, then we'll go back in here. So here we see that's the branch for the k-axis. You know, this is a left multiplication, obviously, but we could change it to right. So let's see. Is this track? No, it's not. This one is left, and it is, what's the name of the output file? Is okay, so that's the pointing vector in E and B. This one's left as well. And it's track. And this one is left. Okay, so yeah, I might have to go through the code a bit more carefully to see if there's a significant difference between the two that might be causing some sort of discrepancy there. But yeah, otherwise I think we're probably pretty close to done with that. Now here's just a short sort of a sketch of a paper that I'm working on based on all of the research that I just showed you. So we have Quaternionic electromagnetic field visualization on S3 with 4D gauge dynamics for P equals E times B. Now this might shed some more light on it. We have the B, the E, and a third orthogonal direction, which is pointing like projecting both points and vectors via the stereographic Jacobian fields. Right, so we get a faithful angle-preserving visualization in OR3. And that's because of, you know, the stereographic projection essentially does that. It gives you faithful projection. So, right, so we're leaving out all of this BIOS Savar stuff. That's basically all that's saying. And then we have, we observe emergent twisting near the projection center and a kind of figure of eight double gauge rotation under anchored frames. So it's suspected that this figure of eight rotation is occurring because we've anchored the frames, which is interesting. Yes. So is there any other so this just explains the basic stuff that we've already seen. And here's some of the equations, which are also quite straightforward. So like I say, this is just sort of a skeleton, really, of a paper that might be written later on. Is there any other points? There's a word for that, which I've kind of forgotten, where if you're projecting from stereographic projections from like 4D space to 3D space, they're conformal. That's the word, and that's why they're angle preserving. So that's why we should be able to project.
Is it like a conform? Excuse me.
Yeah, go ahead.
Is it like a conformal mapping type thing?
Yes, exactly. So that's why we should be able to project the vectors from 4D space. For instance, if we have the B vector and then the E vector is orthogonal to that, then projecting those two vectors from the 4D lines into 3D space should remain orthogonal. So what is E and B generally considered to be? E cross B, it's the inner product of the electromagnetic field and the B field. So would that be usually referred to as H in like the magnetic scalar or something? No, it wouldn't be. I think I've got that wrong. So, okay, so that's where I was getting confused between this. So, so then we have the pointing vector, and we should imagine that this, it's kind of like a third axis. So we should think that the third axis aligns with this E times or E cross B, but in fact, it doesn't really appear to. We notice that there is a slight discrepancy, which is interesting. Might be worth looking into further, but I'm not entirely sure how to do it.
Yeah, according to the original thing, the pointing vector S is the cross product, E is the electric field, and H is the magnetic field auxiliary field vector or magnetizing field. So it's called
E times
Abraham
H.
form. Yeah, yeah. It's a auxiliary field vector kind of. H is the auxiliary field vector.
Okay, so it's different to B, and it's also different to
Yeah.
What's that called, where you have the magnetic potential? Is that not usually defined as H, or is that psi or something? Or not psi.
Yeah, H is the magnetizing field. So B is actually magnetic flux density.
Oh, okay. Right.
So
okay.
So the connection between B and H. B equal to mu times H. Mu is the permeability. So
okay.
So there's a connection between them.
Interesting. Yeah. So I think the whole point of this is, it's purely geometric, but it's still meant to result in dynamic kind of features, and I think we see that with the way the vectors move. But the question is, so we have some of these vectors traveling around. Now, if we look at the orange vectors, which are the electric fields, the electric field is meant to be divergent, isn't it, to the curl at all times? So it has the magnetic field has zero divergence, but the electric field has zero curl. But I'm looking at this and I'm seeing, the orange lines here, I would say, have zero divergence, but they do have curl, or not the orange lines, sorry, the purple lines on the red meridians, they have curl. And the orange electric lines or vectors on the green line here, they they definitely diverge, but they're also rotating around the magnetic field lines, and that is a bit strange. And now that's a direct result of the S3 quaternionic geometry, and also possibly because of the fact that we're stopping this rotation going on here. So it'd be interesting to remove the this how do you say, sort of rotation cancelling effect, and see if the vectors stop their rotation around the lines. But what do you think about that, Rajan? Do you think that the electric field should rotate around these lines, or do you think that that is a failure of the model, or do you have an opinion?
Actually, see the difference between B and H. If it's the same medium, it's about E cross B, right? The same as E cross H. But if the permeability is changing because of the things, then E cross H is not the same as E cross B. So I don't know whether that is one of the things, the permeability or something is changing. Uh,
Mm.
so
You
something
know what,
else is
actually,
changing.
Rajan, we're not even using. I don't even think we have permeability in there as a factor.
Okay. So essentially, you can break down like in electromagnetic thing, induction, right? So you have a coil that, the motor and all those things, or dynamo, they use this kind of thing, right? So it's like a dynamo action. So you have there it is electric coil, the coil. So the current is flowing through the coil, right? And
Yeah,
you have the magnet up and down. So you can have a coil and you move the magnet up and down, so it induces the current. You can
yeah,
do the opposite way. And you can have a current flowing through that, and it will automatically move the magnet inside, right? Because of
yeah,
the induction process. So these
yeah,
things are not coupled. See, in that one, it's not coupled. But if both of them are like there's a current going and you keep changing the magnet inside, right? So now there's a coupling. It's a highly complex level now, because now the electric field is trying to move the magnet, but the magnet itself is moving, means it is creating a back current. So you have called back EMF, which creates a chaos type thing in
right.
the so I think it's like a chaos that's happening in this. I mean, if I can do analogy between that, it's like a
Yeah,
chaotic situation where both the things are moving, and it is back induction and back and forth vicious circle. It's going through, back and
I
forth,
don't
back and
know.
forth.
I would disagree in this instance, because I feel that, like, if we looked at some of the earlier ones, which were trying to like this one,
Uh-huh.
if you look at that, there's a lot of chaos there. Look at how the lines,
Yeah, yeah.
vectors bounce all over the place, and this was the dynamic version, and so it's
Uh-huh.
using some sort of. So I just don't think that was correct. So what we wanted to do was create one where it's following the geometry of the 4D hypersphere,
Uh-huh.
which is very ordered, and
Uh-huh.
so this is, if you look at the way the lines move, they always move in the same way.
Uh-huh.
So I think the way you're talking there about how the electric field, um, if you have a coil and you move the magnet through the coil, then you get an electric current, and if you do it
Yeah.
the opposite way, you get an electric field. So that's kind of, I would consider that a coupling, though. But then I think what you're talking about in the second instance, so I would say that in the first instance, we definitely have a coupling. I'm just wondering if this might. So, like I say, all of this is sort of by simply rotating the field lines here, rotating the
Uh-huh.
hypersphere, and adding the arrows to those lines. I am
Uh-huh.
suggesting that this is a proper model of the magnetic field. But if it doesn't actually straight up conform to how the magnetic field lines usually move and electric field lines, then it's not an accurate model, you know? So that's just what I need. At some point I will need to, you know, prove that one way or the other, essentially. Okay,
So
so
if you look,
yeah, go ahead.
yeah, if you look at point by point, one of them is like point analysis. So
Right.
each point you do that, I think then you sum up the points. So you have to take discretely certain points, sample certain points, right?
Yeah.
Along that line. In that point, you know how they're always orthogonal, the electric field and magnetic field that you can
Yeah.
use. So at that point, what is happening? So the point analysis, if you look at that,
Yeah.
is the magnetic thing changing? And you can fix one of them and
Right.
see how the electric thing is changing and how changing the electric field, how it changes the magnetic field. That's one point analysis. Second case where you do the magnetic change and then how it changes. Then you combine both and see how they interfere, at the point and what happens there. So
Mm.
by point, and then you build up discretely one point here and another point B or point two and point three, and then you kind of synthesize them together. Uh, I think then you get the picture and you see compare that. That's a discrete thing, but even that will help and compare that with this one, right? And
Yeah.
then see, you can do back analysis and see what's happening. So you are kind of dissecting the problem and you are, back analyzing it and seeing that whether it matches that, and you have to, of course, like a calculus, the limit tending to zero, the points come closer and closer. What happens, So then you can get a picture, the whole picture of
Mm.
the whole thing that is evolving. So you are breaking into small things, it's like you know, uh, integrating finite things, and then you integrate them close enough. It's like a series. So if it's close
Mm.
enough, the points are close enough, then it is almost like sort of continuum, which I and Emery are disputing. There is no real continuum. It appears like that, but
Mm.
when it comes closer and closer, maybe closest thing is maybe Planck's distance, or even higher than that, slightly higher than that.
Mm.
When it is more than that, when it is then it's like particle. It's a differentiation between particle and wave. The particle remains particle only at that distance, but then when it merges, it becomes like a wave, or just a field, continuum field. So, I think the particle and the field aspect, I don't know whether it's playing into your thing, the quantum aspect, the quantum field theory type of thing, the quantum electromagnetism is playing into your thing, and it's showing that gray area where it's both wave and particle or the field.
Yeah. I mean, if you see, because such a thing is kind of not modeled in it yet. It's very, like I say, it's very geometric. So
Uh-huh.
it's scale independent. It could be the size of the universe, or it could be the size of an atom or smaller. So, uh, it despite the size, that model you saw just behaves the same way no matter what. So it has no sort of it's not hard coded in that way. What I'm going to do
I,
is, one question we had was, is the p pointing vector the
Mhm.
same as the e cross b, which is
Oh, okay. The difference is the permeability. So you can write S as P over mu or mu naught, which is a permeability. So that's a connection there. Yeah.
well, yeah, but you see the p that we have is we're only saying it
E cross
might
B,
be,
right? E
no,
cross B, right?
s is e cross b.
Oh, okay. So P is the pointing thing.
Right, but we're just saying it's the pointing vector. It's just a guess, but it's actually the orthogonal. Or wait a second, that's actually a bit confusing. What color is P? Let me think. Well, which
Yeah,
this
the
one?
difference.
It gets very
Only
confusing. It gets very confusing, Rajan. So orange.
Oh, you have
is,
P. You have P and S. The connection is if S over mu will be P in your case. So the connection is the permeability.
well, we
Uh,
don't know that for certain. I wouldn't jump to any conclusions just yet.
assumes that. It assumes that.
Okay.
So
So this
that's a
is
factor missing. That's a factor that's missing there.
we don't know that yet, though. But so just keep that in mind, and we'll come back to it. So we know that the purple one here is the B vector, yeah.
Uh,
But if we look here, we don't really have right. So the B is wholly missing from this. And then this cyan one that's winding around is the electric one. So if you look here, that is equivalent to the orange one.
so let me ask a clarification, Christopher, if you don't mind.
No,
So you initially showed, with the girl and everything, there's a loop, right? A loop where the current is flowing. I mean, loop where the magnetic field is, right? A magnetic field loop, and is a current is flowing like a line at the center of that circle, the loop, the center of the loop, perpendicular to that circle. So the current is flowing through that, right? If it's flowing clockwise, then it's rotating
yes,
probably. I mean, if it's going up, probably rotating clockwise, or depending on how the direction is, clockwise or anti-clockwise is rotating. So
okay.
that's the base. That's the unit, right? This unit is repeated at different places, right? Is that right? You have a multiple of these units.
No, the way it's working is very straightforward. It's using this concept so that
Yeah,
as the line goes through, this is the current, and then the left multiplication causes the rotation. But
yeah.
yeah,
But there are multiple things like that. It's not just one loop, multiple loops.
no, but all of these loops are you see they're all like all they're all lines that form like an assembly, so that they're all kind of
Different angles.
no,
So
they're based on the manifold of the hypersphere. So they are what if one is affected, they're all affected because they're an assembly. They're yeah. So
essentially, the current line is just a red line going up and down, right? The current is
no, well,
flowing only in that.
this is actually the magnetic field that stretches to infinity on the top and the bottom.
Oh, that's a magnetic field. Okay.
Yeah. So
So these are the.
in a sense, the left-handed quaternion current that we're talking about isn't really visible here. I was thinking that the blue thing could be another occurrence, but it's sort of implied that there's a current running through these red circles here at the center, sort of like we saw in that animation.
So is that loop of the current at different angles? Is that right? You are different angles. The loop with
Yeah, we'll go in a
respect
circle.
with respect to the magnetic line, the
Yeah,
loops are at different angles.
yeah, infinitely a constant different angle. Yeah.
Okay. So you have to take into account the angle because it's not really perpendicular. So you have to like cos theta or sin theta type
No,
of
it's
thing.
perfectly perpendicular just because of how this works.
Oh,
It's just
okay.
left multiplication, so there's no, you don't even have to think about that. It's kind of so simple. It's all just tied into the whole thing. It's like there's no way of it just is that way. So there's nothing we have to consider. You know, there's no complexity to this. It's all just very simple in that regard.
But they all seem to be at certain angle to the magnetic line, the loops. They're not at same. It doesn't look like they are at the same angle. I mean, not orthogonal. Not all of them are orthogonal. It looks like.
Yes, exactly. That's what I've
They
been
are.
saying. Yeah, that's what I'm wondering. Is that
Yeah.
a problem?
Yeah.
Do you think? I mean,
Yeah.
it's fine with the
Possibly.
magnetic lines. They're
Yeah.
perfectly tangential. But
Yeah.
then we calculate what is the orthogonal vector to that magnetic field
Yes.
line, and it starts to rotate around the line. And I'm wondering,
Yeah.
is that dynamic kind of thing, which is interesting, it's creating
I
all of
think
these
so.
field lines. Is that correct?
I think so. I
Oh,
think that's part of the thing.
oh, great. Well, yeah, we'll
Seems
have
like
to
it,
confirm that for sure. But that's
You have to probably find out the calculation. You calculate and see, are they orthogonal? There's a way to test whether they're orthogonal or not. So if you test that, I think you will get an idea whether that's the problem. You'll get a clarification as to whether that is the one that is creating this particular effect.
Yeah, true. So this kind of to me looks a little bit different to this. I'm not sure if we can say for sure, like the gray lines here behave differently to the cyan lines and the orange lines. So maybe, hang on, let's check. Yeah, we don't have the information for that. So it could be that, so cyan here is P, yes. The gray one is the 4D vector, and the orange one is the electric vector. So if the cyan ones are kind of rotating, and the orange one is rotating. So if we go back here, then we have the orange ones rotating, and the cyan ones that we can't see. Right. Okay. So cyan is P, and then the purple one is S. So E times B. So let's run this again and see if the computer agrees, or rather agrees with us that they are different, not the same. Because we do notice that sometimes the cyan ones flash into view, and the rest of the time they're completely occluded by the orange ones. So is that just an error in the way that the computer is visualizing it, or is that an actual discrepancy? So if we run this, I'll just close those, and we'll see if we get a false or a true, because that's what this is doing. Assume it will say false. Didn't tell us anything, so maybe we need to print this. Yeah. Yeah, false. But that doesn't really tell us a whole lot, because it could be that, you know, there could be an issue with the accuracy for like floats or something like that, because they're calculated in different ways. So it doesn't, we'll have to plot that later and maybe examine how they actually line up or are divergent. So another issue that's sort of related to what we were looking at. So we have this gray 4D vector, yeah? Now, imagine, so let's say we have the E vector, which is the orange one. We have the purple B vector. Now, those are two physical forces, if you like, in reality. And then we have our P pointing vector, which kind of lines up with E cross B. So we'll say that that's another physical thing. And that just leaves us with the fourth gray vector, which doesn't appear to have any physical meaning. So in an attempt to apply a physical meaning to it, what I've considered is you know how we were stopping the rotation of the different fields? Well, what if we use the force that's characterized by this gray vector to like either increase or decrease, but actually let's use it to increase the rotation of the field in some sense, but only at small scales. And the purpose of that is to start to track this thing called the G vector, and in particular, so which is the magnetic moment of an atom, particle, or a nucleus. So this G vector thing. So if let's say you're firing an electron around a collider, according to Dirac's equations, it should have a magnetic moment, so that it lines up again after 2. It rotates like twice, I think, before it comes back around to the start. But what they find is that G factor is actually roughly equal to 2.002319. So there's a discrepancy here, a small amount, but still quite noticeable. And then you find different values for the muon and proton and neutrons and so on and so forth. So I was thinking, and you know, this is kind of related. So this kind of relates to what you were talking about earlier, Rajan. Could we bring in a quantum aspect to this? So if we look at this, yeah. So here's the target anomaly and the Dirac baseline, and the concept here is that as we shrink in size, get closer to like the limit of an electron size, you know, which we'll call 0 for this case because of the speed of light issue around the orbiting the surface of an electron needs to be 0 extent from that point of view. So if we get down to that limit, you know, do we cross a certain threshold? You know, this idea of space-time being granular, and so if we get down to, normally we think of space-time as this smoothly differentiable manifold continuous surface. But if we're getting closer and closer to this quantum scale, we suggest it becomes more granular, which is a bit like you know, this Koch snowflake, where you can imagine this is like sort of smooth, then it gets rougher, and then as n increases, it gets more and more bumpy. So as we go closer and closer to the, or like this coastline, it doesn't look too, I mean, it obviously does look a bit ragged, but as you get closer and closer, it's going to get more complicated. So I think that's what I'm suggesting. So as you get down here.
Excuse me. I
Yeah.
think, yeah, you are talking about a fractal. Is it a fractal aspect?
Yeah, more importantly, it's the fractal dimension, isn't it, Rajan? So
yeah, Hausendorff. Yeah, Hausendorff dimension, it's called. Yeah. Fractal dimension.
Yeah, well, actually, the Hausendorff fraction or value for this is always 2. So its dimension will always be 2, but the actual
2 point something. You
no,
get 2.
No,
when you calculate that,
the Hausendorff dimension is 2, I believe, because it's 2-dimensional. But the actual fractal dimension is 1. Hang on, I've got it here.
Yeah.
1.26186.
Yeah. So Hausendorff dimension.
Oh yeah, it says it there. That's a bit weird.
Yeah.
Okay.
Yeah, that's the correct one. That's correct.
Yeah, you're right. I must have. Sorry, I must have my. Well, but here we got effective Hausendorff. Maybe that's the difference. Maybe there's an effect.
Yeah. Effective. Yeah.
Okay.
Yeah. Okay.
You're getting confused by the terminology. I am anyway. Okay,
Yeah,
well that's fine. So I'm glad we cleared that up. Anyway, so I think we're on the same page here with this. So you've mentioned this before, how we could possibly use a fractional dimension to calculate anomalies. So here I'm just applying that concept to this. So the fractional dimension we'll use is we'll just posit that we're going to use this snowflake, and then we'll run this. Is there anything else to really be said about this? So it's a little difficult to explain, but basically as the edge values increase, meaning as our snowflake is getting more complicated, we are going small. We're getting smaller and smaller, and then these are just the. Well, I think this is probably the most important thing. Proxy doesn't really matter. This is like the perimeter length. This is the where's the. This is the dimension, I think, as it increases. But then we want this difference of G. So if you look here, might explain it better. So the difference of G is like this small discrepancy. So that's what that's our target. So you can see that's increasing, and it's getting ever closer to this 0.002 value, and then we have G. I guess that's effective N. So that's just basically as we add the 2, which is our Dirac baseline, and there's the proxy. So this then will give us a graph which shows the difference of G increasing, and it's kind of asymptotic curve as the value N increases. So even as we get up to 12, it's nearly at the line that we're looking for. And here we just add the 2 in, and then we have the proxy where it's without the baseline of 1 for the. Oh no, sorry, that's the dimension as 1 goes to the limit. So yeah, so that's effectively it, and then we have the sort of sketch of the paper for that. We can see that this use of fractal dimensions appears in quite a number of different quantum physics and astrophysical kind of research in quantum gravity and such, but it hasn't been applied to the G factor of G factor anomaly. So that's kind of good. And the use of the Koch snowflake also hasn't been applied, but really, I mean, that's just kind of a stand-in for whatever the actual granular structure of space-time would be. So you could use an entirely different geometric structure, and you'd probably get a different answer, but it's just meant to be, what's the word? Like instructive or pedagogical, maybe. Exemplary, or an example of what you could do. And that's really it. So I think that's kind of good, kind of linking those things. Here we have more research on the anomalous magnetic dipole moment, and this kind of gives sort of different values. So this is looking at it from a different perspective using the fine structure constant. You also notice that it's talking about this one loop correction because it's a QED thing. So you have to do all these different loops, don't you, and then add them up to get a more precise value. Whereas, so that's why we notice here, I think it's this, we have the electron spin G factor. So for the Dirac, it's approximately 2, but the anomaly, and this is from QED loops, but it's also from experimental values as well, which maybe I closed that window already. But anyway, it's true of the other window. So that's interesting, because like my understanding of it was they send the particle around the collider and it's supposed to come back into alignment after one rotation, but it whatever, it either does 2 rotations, but there's a slight discrepancy. But how do they measure that, the fact that the dipole moment is off? Do they have to collide it? Because this appears to look like some sort of interaction, which would suggest that there needs to be some sort of collision. But maybe there doesn't. Maybe just the mathematics requires these kind of things in order for them to get their equations. But then in the particle collider experiments, they can measure it some other way, or do they need to actually collide it in order to measure the spin? That's what I don't know. Do you have any?
Yeah, there is that. What is that called? Trying to remember the famous instrument. I can't remember that.
Like Wallace or something?
It is used a lot. I mean, that's the fundamental of the magnetic thing.
Yeah, I
That
think
acts like a sensor. I'm trying to. I'll get it after a little while. I know it's missing me right now. But it is the it uses a tube, but you can use like a sensor. So they will have sensors everywhere, and that sensor will give the input about the it will give the input about the what is the magnetic dipole moment at each, almost like each point or closely spaced points.
Oh, really?
And they'll have, I think they'll have these sensors.
Wow.
And these sensors will give feedback, and then it corrects that. It keeps, I think so. I'm not completely sure. We have to go into
Okay.
the, but in real time, it can keep correcting the trajectory, so that they will collide the proton. You're talking about the proton-proton bombardment, right? They have to come at fast the speed of light, relative speeds. They come, and when they come around, they have to precisely align, and so that they will, when they collide, the 2 protons, they will create all the particles, right? That's the fundamental thing. But they have to correct the trajectory continuously, because, like you said, it will deviate because of this effect. So I think they will have that particular. I don't know why. Yeah, I will know it a little bit. I mean, that's one of the main sensors, but there will be other sensors also. So there are a lot of sensors, along the path of the collider.
Well, definitely look that up, Rajan. If you can find it, I'd be interested to see it.
Yeah.
So the final thing then would be, if we are going to use these magnetic field models to generate for like geomagnetic field lines, where's it gone? Is that? Oh, it's gone. Oh no, it's this one. If you are going to use it for the purposes of geomagnetic fields, that's closed. So then we're going to need, first of all, we're going to need data from the, we'll close this. We're done with that. We're going to need data from the Earth's, some sort of sensors, like, space data, kind of a satellite or something, and then get the model for it. And we'll wind up with something like this. This is like a simple representation of it. This is not how it would actually look. And then you can imagine that we have our field lines. So here we have meridians and parallels, I guess, but on like an S2 sort of version. And then, so if we can map this onto that, and then multiply this field against field lines, then we would be able to distort the field lines based on the power of the observed magnetic field or model. And that might be useful then to generate a more complicated geomagnetic field model that sort of matches real world observations. So I think that's really it. This looks like a very good website from just from the point of view of how it's laid out, and it looks like it has some good information which might be useful. So that's really it. We'll leave it there. One final point I suppose we should make is that Unzicker recently did a video, Origin of the Speed of Light. Close these. And in this, and he's talking about quaternions again and tangent spaces. So this video, he basically we'll lower the intro music, just so fantastic scenery, really. I mean, but so he's got this idea of like a wild speculation, which is so he's talking about quaternions, and there of course that's a bridge in Dublin actually where he wrote the equation down. Yeah, you can go visit that. He actually
in Ireland. Does he stay in Ireland or
he was Irish. Rowan Hamilton, yeah, he was Irish. He lives down the road from this bridge, and he kind of carved it into the wall, and then and there was loads of people like around watching it. So this is not the original thing. That's long gone. It's worn off, but so they just have this up to commemorate him. I've actually been to that bridge. So yeah, and he also invented the dot product, partial differential equations, and quaternions obviously, and a bunch of other stuff as well. Well, the Hamiltonian. So a lot of these things, like, you know, you consider like how much these objects are used in physics today. Without Hamilton, it wouldn't have really been that possible. I'm sure someone would have figured it out eventually, though. So here he's talking about we have a hypersphere, which is the quaternion sphere, and then a tangent plane. And then he talks about you could project like so that he has this sort of complicated idea of a light cone, and well, you might as well listen to what he has to say. Maybe he'll explain it a bit better.
From the universe is light and is in that tangent space. What if the light cone is just the tangent space of, say, the three-dimensional unit sphere?
You see this? Okay, so that's what he's talking about. Why would a light cone be the tangent space, though? Because, you know, the tangent space is what? Flat, generally. Like if we think of this like a sphere, an S2 sphere, tangent space is going to be a flat plane. So how is that a cone? I don't really know. I mean, maybe when he's moving it up to a higher dimension, but it's still just, it's going to be a space then. It's going to be a three-dimensional space, which is also not a cone.
And yes, of course, in that case, you would have deviation, the greater.
Oh, yeah, so here he goes.
Distance to the past, the bigger the deviation from.
So he's bringing in time into it. I don't know how he's doing that. I assume he's thinking that because he's got a four-dimensional sphere, that one of the dimensions is time. But yeah, you know what I mean?
Reality. You might even speculate about the Hubble redshift.
Like usually when we talk about spatial dimensions, you know, if you've got a 4D spatial dimension, that's going to be different to a time dimension. And it's not always the case. There are ways to link them up, but if you're going to do that, you're going to have to specify exactly how you're doing it. So here he's talking about Hubble redshift.
Coming from that effect. But as I said, need to
So that's basically, my model with the stereographic anamorphic projective cosmology, where you project the galaxies from the hypersphere onto the tangent space, and the anamorphic distortion causes the Hubble redshift.
Reason why we have constants such as the speed of light provides.
Now, so I don't know why he's saying that just because we have a Hubble redshift that results in the constants of speed of light, because one doesn't seem to affect the other. You could say it's the other way around, that the effect is being caused by. Also, if you're removing the idea of expanding universe in this model, I don't know if he's aware that that's what would be the case, but maybe he's talking about the spheres expanding on the tangent space, which is actually a different theory to mine, because mine would have a static sphere, but and that is promoted but in other areas. So, but yeah, so I just don't. Yeah, I suppose if he's coming from it that way, there might be, but he doesn't really mention that. So
this strange speed limit occurring in nature, and yes, a mathematically cogent reason would be every manifold has a tangent space. Of course, in terms.
Why does he say every manifold? Is every moment in time there's a new manifold, and that has a tangent space? So that would imply that the sphere is expanding. So the next moment, it's a new manifold because it's a bigger sphere, possibly.
A lot of problems arise, such as how can we understand space and time and the qualitative difference between space and time.
So he's concerned here about the qualitative difference between space and time. His solution is bringing up new problems because, he's dealing with quaternion space, which is, they're all spatial dimensions, but he wants to treat one of them as time. So he's got a problem there.
What does this quotient, meters per second, tell us? What's time after all? Why we have?
So he's going off into it, like, I don't know.
Time itself.
Metaphysics and philosophy here.
Goes back to Hamilton, because he said quaternions, quaternion algebra, there's one real dimension and three imaginary ones for purely mathematical reasons.
Yeah.
So you might think about the imaginary directions representing spatial directions, but still you have a problem to qualitatively justify the appearance of time. But it's nice to speculate the tangent space being the light cone, because once you multiply.
See, he's talking about a flat plane being a cone. So, well, yeah, I mean, if you were to imagine the sphere and then you have a plane here, and then you kind of wrap it around the cone or the sphere in a certain way, you could generate like a bunch of tangent lines, which would make a cone. But I don't think that's what he means. Maybe he does.
No, so you have like a hypersphere, and then you have the flat thing.
Yeah.
So it's giving like that, something like that.
What? Well, how does a flat plane?
Like a cone. So
Yeah.
it's like a cone, and then you have the sphere sitting on the what do you call first term of the cone, or the base of the cone.
Okay.
And you have the apex down, and the base of the cone is up there, and the sphere is sitting into the cone, like a ice cream scoop of ice cream type thing.
Yeah, I know, but that's not a tangent space then anymore, is it?
Yeah.
Because you can say the cone is tangent to the sphere at that point. But then, but if you did a stereographic projection from the sphere then onto the tangent space, and the tangent space is a cone, so the results would be.
He's talking about tangent to the sphere. There are many tangents, right? The tangent plane.
Yeah.
There are many of them, right? Because depending on where you take them, which point, you get a tangent plane at that point in the sphere. So that one, and then you take another one on the opposite side, right? So you have another tangent, but they are, and you take it at a level that it is at an angle. It's not at the diameter. I mean, so the two radii, and then you have these things coming like that. So that's still a tangent plane. I think that's what it seems like that.
No, I don't think a
And this,
cone would be defined as a tangent plane.
not the cone, but the side of the cone, which is a tangent, a plane. So so many. So you have a line, from the sphere, which is
Yeah.
tangent. So you
Yeah.
essentially a tangent line, okay,
Yeah.
tangent lane making up a plane. So, but it is curved. So I don't know how that is,
Yeah. Yeah. It's
each
interesting.
one,
Use
yeah, each one. So each one is tangential plane that is,
Well, it's
that
not a.
diverges.
Yeah, it wouldn't each one could. Yeah, like I said, it would be building up some sort of line bundle or whatever or
Yeah,
plane.
it's curved. It's curved. But in the each curvature, you have a point, and they create a plane. So you have many, many sections of the plane.
Right, but we're just speculating. I mean, if that's what he means, he should
Yeah.
say that
You
probably.
should clarify that. Yeah, you
Yeah.
can ask that.
But so, and even if he does mean that, there's other sort of larger things that could be a problem. Like if we look at the diagram so technically, well, maybe because we've kind of skipped through his video. So
If we live in a curved three-dimensional manifold, such as the three-dimensional unit sphere, three-dimensional unit sphere, or Quaternion sphere, and this speculation is also.
So he's saying, what if we live in a three-dimensional unit sphere? Again, that's a little bit different because the hypersphere is technically four-dimensional, or at least it lives in a four-dimensional space, and technically
Projection. You're talking about a projection.
yeah.
So you keep projecting onto a plane. That's what he's talking about.
No, yeah. Well, but if it's a 4D projection, it's going to be not just a plane, it's going to be the tangent space.
3D. Yeah, it will be 3D. And then
Yes.
you are project that again onto a plane. So it is a double projection.
No, you don't. There's no plane involved at all, Rajan. You see, yeah.
Because
So
he's talking about flat
sorry, what?
in a topological. He's saying S3 may also be a flat in a topological sense. How does it become flat?
No, yeah, exactly. But okay. So, but he's saying we kind of live on the sphere, and the sphere will be curved, obviously. But the tangent space is flat. So that was the whole thing about the anamorphic perspective cosmology. It's about, it explains why the universe is flat.
The universe is more clear, very, very distinct, because you have hypersphere, then you have a tangent plane.
Yeah.
So that's very, very distinct. But he is talking something else. He's talking a subtle aspect.
Let's give him a chance to say
the fact that we have to find first principles explanations for the constants of nature, such as Planck's quantum of action and the speed of light. And if you imagine that we live in a curved space, then automatically, as a mathematical concept, you have the tangent space, which you might imagine just a sphere in a touch surface and a touch.
So there you go. So we have the sphere and we have the tangent plane.
That's curved, right?
What?
Oh, the tangent is just at one point. You have he's creating a plane out of a point almost.
Yeah.
And that's a flat one. Okay.
Yes. So I'm just confused about how this becomes a cone.
Oh, in your thing, you are North Pole and South Pole, right? So you have North Pole, and the South Pole is where you are putting your tangent plane. But he's putting in at all levels.
Wait a second. You're wrong there. Okay.
Huh?
Start. Let's say this tangent plane is on the South Pole, yeah?
Yeah.
Yeah? Let's say the tangent plane is on the South Pole.
Yeah.
Right? Okay.
Yeah.
Now, at the North Pole, we're not going to have another tangent.
No. I'm not saying that. I'm saying that your tangent plane is South Pole. That's it. but he has many built on the side of the.
How do you know that though?
electrode.
He's only showing one.
He's showing, yeah, he's showing at an angle, not at the south pole.
So what?
At some arbitrary point, he's drawing a plane.
Okay, so you
He's
think
having
that?
a plane.
Okay, but he's talking about a tangent plane, a plane. You see?
That's a plane, yeah. He's showing that there. The red.
He's not saying multiple planes. He's saying a plane.
No, that's specifically he considering one aspect, and then
Okay, well then let's let him talk and see if he says that. Because
okay.
We could not perceive reality, but just look straight into the tangent space.
The tangent space.
What if all the information we can gather from the universe is light and is in that tangent space?
That tangent space.
What if the light cone is just the tangent space of, say, the three-dimensional unit sphere?
What is the tangent space of the three-dimensional? Now, see,
you should build up. He didn't build up he should build what he's saying from that statement to this. He should show different geometry, because he's talking about different geometries, the evolution of geometry, but he's not showing that picture.
Exactly, because I mean, we could, you could start being charitable to him and say, well, when he says a tangent space, he doesn't mean like a specific one. He's just talking about all potential possible tangent spaces. But that would be the space of tangent spaces, wouldn't it? But anyway, so maybe that's what he means, but he's just not being very clear. I'm not sure.
So you can ask for clarification. Is he talking about evolution of tangent spaces that makes up that cone? No.
What cone though? Because even if you had all
the light cone,
can you let me finish, Rajan?
Okay.
Even if you had all the tangent spaces, it still wouldn't make a cone, like an actual geometric cone.
That's what we had to clarify from him.
Well, I mean, he's made the video here, so he should explain it.
And yes, of course, in that case, you would have a deviation. The greatest distance to the past, the bigger the deviation from real.
Right. So somehow, so basically, this is about the first. So looking further away on the tangent space is equivalent to looking further into the past, which is what the light cone is about, essentially, isn't it? If you look back in the past, the light cone is going to get smaller. So so you could say there's some deviation between the current state of the light cone and the earlier state. The question is, though, so that's that. I mean, on cosmological scales, then that would be the Hubble redshift. Kind of, but I mean, that's sort of a separate issue, I would suggest. I mean, you'd have like the deviation is like the thing is quite localized, and then as time progresses, it gets less localized. It spreads out. So what you should, when we look further back in time, instead of it being more spread out by the stereographic projection, it should be tighter, which is not what we see.
I mean, is it like the epochs? They show the epochs like a light cone or something, right? The epochs of the universe, at least the Hubble expansion in terms of the light cone.
Yeah. Right. So what he's talking about then is when he's saying you're not looking back in time into the light cone. We're looking crossways, like we take a cross section through the light cone, and that's all of space at this snapshot. And we look out, and we see the light coming from like the boundary, the observable universe. So therefore, the light cone here is really more he's talking about the expansion of the universe. Yeah, that makes sense.
It is kind of manifesting that expansion, so to say. It's kind of reflecting that aspect.
Yeah. So he brings up the redshift then.
Coming from that effect. But as I said, we need a reason why we have constant such.
Okay, so that's kind of it. I thought that was interesting anyway. So Right, we'll kind of leave it there. Yes. So, what do you want to do? Do you want to? Do you want to
Yeah.
take
So
a quick break, or?
yeah, we can take 5, 10. You want to take a break, 5, 10 minutes?
Yeah, just yes.
And also we
Even a
may
few.
want to finish up. Somebody is coming, so I don't know whether they will. I have to check whether they have texted me. I have to change something in my car, so they're coming here.
What
But
time
I
do
don't know
you want?
when they will come. Yeah, they're giving a long, like 11:30 to 4. I mean, which is like half an hour, anywhere from half an hour to oh, let me find out. I think they see half an hour to 4 hours.
Okay, so you've got quite a
Oh,
wide range there.
okay. So they are already on the way. So we should probably wind up so that
Okay,
I can
all right.
maybe
So
we can
do you
wind
want
up.
to talk about it? Do you want to discuss? Because you have a good bit of work that you were going to show.
Yeah.
The
So if you want to take a break till they come, it could be or I will know. Let me see. Yeah.
or do you need more time to go through your stuff? Do you want to do it next week, or do you what do you want to? Or not
Yeah, I
next
thought
week, I
about
mean the
drink.
next time.
Yeah, we can. Let me see. But we are talking about UFO. But we can start that and add the UFO thing also, right?
Yeah, like
I
yeah,
can
no,
start my thing.
exactly.
I
Like
can start.
that's just sort of the main. That's well, not the it's the title thing, but you know,
Uh-huh.
there's always like space for like other discussions. Usually, it'd be good if
Uh,
they're related, but they don't have to. It can be just like whatever your research is at the time.
yeah.
So I was thinking like today would have been would be good because it's kind of I don't know they
Yeah.
both kind of match, don't they?
Electromagnetism.
They're like
Yeah.
it's like electromagnetism, and I think what you're doing is oh
Similar.
well, what is it, Rajan? You're
Before
looking
that, things before that. Yeah.
yeah, it's more
It's-
quantum cosmology and stuff. So
Yeah. It's a start of the whole thing. Early universe where
hmm,
everything was totally different. So
yeah.
yeah.
Okay, well, so yeah, anytime you want to, we can cover that next time.
Yeah. Okay. Okay. Thank you. So thank you, Christopher. Excellent presentation. So we'll continue next week.
Okay, thanks. I'm just gonna.
Thank you. Yeah. I'll talk. Yeah. We'll discuss in between. Yeah.